Alright, welcome back. This video we're going to be talking about the mean value theorem. So in the last video we introduced the derivative rigorously, and now we're going to you know, talk about a major theorem involving the derivative. So the first thing to talk about is local extreme values. So local extreme of a function. So f has a local max or n at a point A in D if and only if there is some delta greater than 0 such that for x in D with x being within delta of A, we have f of x less than or equal to f of A. Or, in the case of the minimum, we would have f of x greater than or equal to f of A. Right? So for max, it's 1, the inequality sign goes one way, and for the minimum, the inequality sign goes the other way. And this should be fairly intuitive, right? This is just saying the idea of the term local, and this is an important term if you study deeply into sort of topology or analysis. The idea of the term local just means that it may not be the largest value that the function obtains overall, like over all of its domain, but compared to values very close to that point, it is, it is no more or no less than that one point. So, graphically, right, you have a local maximum looks like that, or a local minimum looks like that. Because neighboring points are either greater than or equal to, or less than or equal to. Okay. The next thing is we are going to recall the interior of a set D, right? So this was introduced, in the topology series, but here we're just going to rephrase it in a analysis framework. Okay, so a point A is in the interior of D, which is denoted by D with a little circle. If and only if there is delta greater than 0, such that the entirety of the interval a minus delta to a plus delta is contained within D. Okay, so this is saying essentially interior points of a set D are points such that I can fit some interval around A into the set D. Some open interval, I should say. Of course, if you can fit a closed interval, then you can fit an open interval. But okay, so that's it for definitions. Now we can get into the first the first result, okay? And this is going to say if f is differentiable at a local extreme point, which is we're going to denote it by mu, and this point is also in the interior of our function's domain, then the derivative at that extreme point is 0, right? So you may be familiar with this result, right? And graphically, as you can see, if you have a local maximum or a local minimum, the slope at that point is 0. Okay. And the idea is just by casework, well, one case for if it's a local maximum, or one case for if it's a local minimum. So case 1 is going to be where it's a maximum. So so first of all, since we have a local extreme, right, by definition of a local extreme, we have some delta where for any x values within delta of a, or within delta of mu, rather, then f of x is going to be less than or equal to f of mu, right? So by definition of local max, there is delta greater than 0 such that for x in D with x minus delta, sorry, x minus mu being less than delta, f of x is less than or equal to f of mu. So let's say we pick an h value, which is between 0 and delta, then mu plus h mu plus h minus mu, the absolute value, is less than delta. So, and also since, an important thing to note here is that since we've chosen mu to be an interior point, we don't have to worry about sort of like the whole cluster point thing from the last video, right? The fact that it's an interior point, we can, if need be, right? I really, there should be two delta values here, right? If need be, we can restrict delta to be small enough such that any x in, actually, sorry, ignore what I've been saying, since we're already assuming our x values are within D. But also just with picking an h, right, saying mu plus h might not be in the domain, but since we have an interior point, we can choose a delta small enough to guarantee that mu plus h would be in the domain. So that's what I was trying to say. So since mu plus h, right, mu plus h serves as an appropriate x value for saying that f of mu plus h is less than or equal to f of mu. And then we can move f of mu to the other side, and we can divide both sides by h, because h is a positive quantity. So we get that f of mu plus h minus f of mu over h is less than or equal to 0. Similarly, if we instead choose h to be negative, then f of mu plus h less than or equal to f of mu will imply that f of mu plus h minus f of mu over h is greater than or equal to 0, right? So just to elaborate, the sign flips because of division by negative quantity. Thus, we can look at the left and right-hand side limits of this difference quotient, right? So the limit as h approaches 0 from the right, meaning for h taking on positive values and approaching 0, this must be less than or equal to 0. And this essentially just has to do with the continuity of f, right? Since we know f is differentiable, f is differentiable, and we proved last video that if f is differentiable, then f is continuous. So limits preserve order. That's all that we're using here. And so as we go from the right-hand side, right, the limit is less than or equal to 0. And as we go from the right-hand side, or sorry, left-hand side, the limit is greater than or equal to 0. But this limit exists and therefore equals the left and right-hand side So in other words, right, this limit exists, and it is the derivative of f at mu. So the derivative of f at mu is less than or equal to 0, and the derivative of mu is greater than or equal to 0. So the only possibility is that the derivative is 0. Okay? So that was that was only the first case, but thankfully we don't have to go through much of the second case, right? So the second case is where you have a minimum. And one way to argue is that it's going to be the same idea, right? The same proof, except that here and here, your inequality signs are going to be flipped. But in the end, you're going to have that f prime of mu is both less than or equal to and greater than or equal to 0, which means f prime of mu is 0. So you could argue that way. Or you could say, take g of x, or I'll just say g equal to the negative of f. Then if f has a minimum, then g has a maximum. And therefore, g prime of mu is going to be 0. And then f prime of mu is going to be equal to negative 0, which is 0. So that's all we have to do. All right, so that was the first result, and probably took more time than I wanted to. So now we're going to get into the real theorems, right? So we're first going to start with what is known as Rolle's theorem. Rolle's theorem says that if f is a continuous function, a to b on the closed interval ab, and f of a equals f of b equals 0, and f is differentiable on the open interval ab, or I should say at least, right? So the thing here, right, is that we don't need f. F doesn't necessarily have to be differentiable at the two endpoints. That's all I'm saying here. So if these conditions were met, if f is continuous, if f of a equals f of b equals 0, and if f is differentiable on ab, then there is mu in the open interval ab such that f prime of mu is equal to 0. All right, so the proof, I'm sort of just going to argue graphically, because the graphical proof essentially is just the guiding light for the actual technical proof, which isn't very involved. So you have 3 cases. So one is if f of x is just equal to 0 on AB, right? So f is a constant function, and as you can check yourself, constant functions have a derivative of 0. So, right, we could just take any point between a and b as mu. So this is sort of, just a trivial case. The second case is if f of x is greater than 0 for some x in AB, right? And so the idea here is that right here you have, let's say, a and b, oops, a and b, and your function value is 0, and then you have some x value being greater than 0. Well, you know that right, what should I say here? You know that f has to increase from a in order to get to this point, and not necessarily all at once, right? It could increase and then it could decrease, right? But it has to be increasing at some point. And it also has to decrease at some point from here to b, right? a more rigorous way of saying this is, the intermediate value theorem says that between, so let's say this is x, we'll put it on this axis. So between a and x, f is going to achieve all the possible y values between 0 and f of x. And between x and b, f is also going to achieve all the y values between between 0 and f of x. And so essentially you have to have a local max on the interior, right? Because at some point you will be increasing and then you have to start decreasing, right? And essentially what this is trying to say is that your max can't be on the endpoints, right? Because if you had a maximum, right? Well, if the maximum were at an endpoint, right, that would mean the maximum is 0, which contradicts, well, I guess it's a local maximum. You would have a local maximum at an endpoint, right? Sorry, the argument is slipping. So sorry, it will be a global maximum, right? Because and it has to be on the interior, right? Because first of all, f is continuous, so it has to be bounded, which means it has some maximum value on this closed interval. And it can't occur on the endpoints because the endpoints you have 0 and 0, right? But you know you have, just by casework, in this case, you know you have some function value which is positive. So all we're trying to say here is that we're narrowing down, it's partly narrowing, but we know the maximum must occur on the interior. And the interior is where we can take a derivative. So we can take the derivative at that point. And a global maximum must also be a local maximum because your delta could be essentially as big as you want, right? Any function value will be less than or equal to the value at that maximum. So the derivative at that maximum value is 0 by the previous result. Okay. And the third case is similar. If you have some function value which is negative, then you have a minimum, and you can take the derivative at that minimum, and that minimum occurs on the interior. So it's just a similar proof there. Okay, now we're on to the final theorem here, which is the mean value theorem. The mean value theorem is just a generalization of Rolle's theorem. And it says that if f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists value mu on the open interval AB such that f prime of mu is equal to f of b minus f of a all over b minus a, right? And this is, this can be understood as the average rate of change of f over the interval a to b, right? It's the difference in y values divided by the difference in x values. Okay? And so the mean value theorem is saying we can find some point where the derivative of the function is equal to the average rate of change. So the way we're going to do this is essentially reduce the function f into a function which we can use Rolle's theorem on. So the way we do that is first finding the line connecting the point a comma f of a and b comma f of b. This line is given by g of x equal to f of a plus f of b minus f of a over b minus a times x minus a. And notice that g prime of x is identically constant and equal to f of b minus f of a over b minus a, right? Of course, I haven't proved as an example that the derivative of constants or linear functions are behave as we would think, but the proofs are very similar are very easy in those cases. And at the end of last episode, I gave that as an exercise, so I'm assuming that we have established that. So now let h of x equal f of x minus g of x. Then h of a equals h of b equals 0, right? Because at a and b, f of x and g of x have the same value. So when we subtract them, we get 0, right? And g of x is a line, right? It's a linear function. Well, not a, now I'll just say a line. So it is continuous. The difference of two continuous functions is continuous. So h of x, or I'll just say h, is also an element of CAB. So by Rolle's theorem, there is some mu in the open interval AB such that the derivative of h at mu equals 0, but the derivative of h is equal to the derivative of f minus the derivative of g, right? Of course, again, I didn't prove this, but I left it as an exercise. This is a typical derivative rule. And g prime of mu, as we've already stated, is this expression, f of b minus f of a over b minus a. And so this finishes the proof, right? We can just move this term to the other side, and we get f prime of mu is equal to the average rate of change. And so that is the proof of the mean value theorem. So the next video will be the last of the real analysis series, at least for now. I may return to more advanced topics at a later date, and we will talk about the fundamental theorem of calculus. So I'll see you then.